All right, well, welcome back. So we're going to begin talking about flip-flops in earnest. So flip-flops, remember, are these edge-triggered memory elements that will let us store information, but based on the transition of a clock as opposed to a clock simply being high, saying go ahead and remember the input. These devices, when a clock changes from low to high, they will capture the input at that instant and then remember it until the next time the clock makes that transition. So these things are called flip-flops. And there's numerous stories why they're called flip-flops, but one story is that the way they were originally built used components that actually made a noise when they changed state, and the noise sounded kind of like a flip or a flop, depending on which way the device changed, and that's just what the engineers called them. We mainly work with three types of flip-flops. The book talks about a fourth one that you actually don't encounter that often. So we'll mention it, but we're mainly going to work with three types of flip-flops. The first one is a D flip-flop, and I'll just label it with a D. And there's an input called D, and there's an output Q, and there's a clock. All right, so we're going to develop a number of conventions related to these types of devices, and you'll want to, definitely put these down in your notes. We'll use them a bunch in practice problems in labs and so on. So we'll encounter them again and again, but we'll just start developing some of these conventions right now. So remember, these devices are triggered based on a change in the clock input as opposed to a level. We indicate that with a little triangle sitting right here. That triangle means that this is an edge-triggered device. Things will happen when the clock changes, rather than just when it's high or low. So this is a D flip-flop. This is the device that we developed originally using two D latches, and then the clock and the inverted clock going in. So the device is drawn like this. Let's make a table describing the behavior of this. And this is pretty typical for what you'll see. We'll have an input D and an output Q. And the idea is we understand, since it's a flip-flop, that things only happen when the clock changes. And so we don't actually list the clock as an input. The clock is the thing that drives the action. And so if D is a 0, when the clock changes, Q becomes a 0. If D is a 1, Q becomes a 1. And we usually indicate that this is the new value of Q after a clock tick. So you might see it written as Q plus, or possibly Q star, or maybe sometimes QN plus 1. And the reason is that sometimes we'll have values of Q in this truth table because the new value of the flip-flop will depend on the previous value. So for a D flip-flop, there's not a lot of ambiguity. If D is 0 when the clock ticks, Q becomes 0. If D is 1 when the clock ticks, Q becomes a 1. So the output just matches the input, but only on that clock edge. And with a timing diagram, again, remember, D can be doing all kinds of things. And when the clock is low, the output is stable. Let's just suppose it's low. At the moment that the clock changes from low to high, the output will match whatever D is, and it will stay there until the clock goes low and again goes high. And at that point, if D was low, for example, then the output will go low. And the positive edges of the clock, that's what marks when the action happens. Everything that happens before or after, irrelevant. All right, so that's a D flip-flop. The next type of device is called a T flip-flop. So a D flip-flop, we can think of that as a data flip-flop. A T flip-flop, we can think of as a toggle flip-flop. And the main thing this does is change values between 1 and 0. So it's got an input labeled T, it's got the clock input, and it's got an output Q. And here's what the table looks like for a T flip-flop. If T is 0, then when the clock ticks, the new value of Q is the same as what the previous value was. If T is 1 when the clock ticks, the new value of Q is the complement of the previous value of Q. So in other words, if we set T to 1, then when the clock ticks, the output flips. If it was currently a 0, it'll go to a 1. If it was a 1, it'll go to a 0. So a timing diagram looks something like this. Let me put the clock on top. And so we're only interested in what happens on these clock edges. And let's suppose that Q is initially low. Alright, if our toggle input is low, clock ticks, nothing happens. If our toggle input is high, then every time the clock ticks, the output changes. If the toggle input goes low again, then when the clock ticks, nothing happens. Right? So different from a D. The T flip-flop is basically saying, should we leave the output stable or should we flip it? If the T input is high, each time this clock ticks, the output flips. It goes from low to high. Next clock tick, it goes from high to low. Next clock tick, it goes from low to high. But on the next clock tick, T is low, so the output doesn't change. Back here, T was low, so on the clock tick, the output didn't change. So the clock ticks are still happening, right? In a large-scale system, you have a clock. It's going everywhere throughout all the circuitry. It's constantly running. It never changes. It never stops. It never slows down. But not everything responds to the clock in the same way, right? This T flip-flop, if the T input is low, it basically ignores the clock. If the T input is high, then when the clock ticks, it toggles the output. So that's a T flip-flop. All right, an SR flip-flop, this is the one we don't usually encounter. It has an S and an R input and a Q output and a clock. And you know, a lot of times we don't even draw the clock line. We just put this symbol saying there's a clock going into it, but we understand flip-flops are clocked devices. But all the action happens with S and R. So what does this do? Well, if S and R are both 0, it ignores the clock. The new output of Q is the same as the old. If S is 0 and R is 1, that's our reset state. The output goes to a 0. If S is 1 and R is 0, that's the set state, and the output will go to a 1. And then if S and R are both 1 and the clock ticks, well, we're simultaneously telling the flip-flop that it should be set and it should be reset. And that's an ambiguous set of instructions. So what's it going to do? Well, it depends. Sometimes this is called a forbidden state. It's a pair of input combinations that we might just say is never going to happen. Or the data sheet might specify, you know, set takes precedence, or maybe reset is dominant, or maybe it just freaks out and starts oscillating. So we'll usually just avoid this state where S is 1 and R is 1. Now, if you look at some problems in the book, they will give you specific behaviors for the situation, and that's what that flip-flop would do. But it really depends on the device. But the reason that we don't worry about SR flip-flops very often is because there's another kind of flip-flop which is more useful, and that's called a JK flip-flop. Possibly named for Jack Kirby, who invented the flip-flop. And so this is almost the same as an SR. It's got a pair of inputs, J and K. It's got an output Q. And the behavior is similar to an SR. If both inputs are 0, the output is stable. It ignores the clock. If J is 0, K is 1, that's a reset state. If J is 1, K is 0, that's a set state. But for this device, if J and K are both 1, it acts like a T flip-flop. So JK does, you know, everything that an SR does, and it also does what a T does. So it's a really powerful flip-flop. It's probably the most popular version. A D flip-flop is very single purpose, right? Just latch this data bit. Boom, just save it, save it, save it. But if you want a more general purpose device, usually we go with a JK. All right, so let's talk about some of the realities of flip-flops. So one reality is most flip-flops have a pair of outputs, Q and Q bar. And Q bar is just the opposite of Q. So if we drew D flip-flop and we looked at the Q bar output, it would start off high, it would go low here, it would go high here. If we take our T flip-flop and we look at the Q bar output, well, Q would start off high, and at this point it would go low, and then high, and then low. And it just does the opposite of what Q does. And the reason most of these devices have a Q bar is because you get it for free, right? When you have your cross-coupled gates, one of those gates is going to output Q, but the other gate's going to output Q bar. So whatever value I read here, generally I'll read the opposite value here. So you kind of get it for free. All you have to do is farm that output to a pin on the chip. So and it's useful to have the inverted output, so we don't have to actually put an inverter into our circuit. So most of these flip-flops have both a true and a complemented output. So the devices we've been talking about change when the clock moves from 0 to 1. This we consider to be the positive edge of the clock because it's going from, say, 0 volts to 5 volts. And so these are what we call positive edge triggered devices. But we can also design a flip-flop which makes its action happen on the falling edge. In other words, when the clock changes from 1 to a 0, these are called negative edge triggered. And you can find devices of both types, positive edge triggered, negative edge triggered. If we have a negative edge triggered device, we can tell it from the block diagram because there'll be a little circle on the clock input. So we'll have our triangle there saying it's edge triggered, but the little circle says it's negative edge triggered. Whereas if we have that triangle going directly to our clock, that's positive edge triggered. All right, additionally, you can find other inputs on here. For example, some of these devices will have a clear input, and some will have a preset input. The idea of the clear input is to force the output to 0, and the preset is to force the output to a 1. And these may be synchronous, or they may be asynchronous. A synchronous input means it only does something when the clock ticks. So, you know, if J and K are both 0, the output's supposed to be stable. If I have a synchronous preset input and I put a 1 in here, the next time the clock ticks, this will go up to a 1, regardless of J and K. Or if I put a 1 into my clear input and still a 0 on preset, the next time the clock ticks, this will go down to a 0, regardless of the values of J and K. So that's a synchronous preset, a synchronous clear. And asynchronous means that if I set the clear line to 1, the output immediately drops, regardless of what's going on with the clock. So in between clock ticks, normally the device is stable. But with an asynchronous clear, as soon as I put a 1 into that, the output drops right away. And with an asynchronous preset, if I put a 1 into this, immediately the output goes to 1, regardless of the clock. we use this, for example, if we have a bunch of flip-flops and we want them all to be set to 0 in the beginning of the circuit's life, right? When we first apply power, we could build a circuit that shortly after power becomes available, sends a pulse into all the clear inputs. And if those are asynchronous, boom, all our flip-flops will get cleared to a 0, and now they're all in a known state. So if you look at parts lists, you can find things like a dual negative edge triggered JK flip-flop with synchronous clear and asynchronous preset, right? Which means it's a device containing two of these things. They're JKs, they're triggered on the negative edge of the clock, and one of these inputs pays attention to the clock and the other one doesn't. And you can find lots of different variations of these, and they're all basically the same kind of design. They're built up from that idea of taking two latches, putting in a clock and an inverted clock, and hooking them up in that sort of two device configuration. And we can look at timing diagrams for these and so on and so forth, but they all basically are variations on this. All right, so let's look at realities of behavior. So let's go back to our data sheets. And let's look at a flip-flop. So we'll look at the 7474. That's a dual positive edge triggered D flip-flop. It has a pair of these D devices. We can see there's a clear input coming up here. That's CLR1. And there's a preset input going in here. And you see there's bubbles on there, so those are active low. So here's the truth table. If the preset line is low and clear is high, it doesn't matter what the clock's doing, it doesn't matter what D does, the output goes high, and the complemented output goes low. So that's where the preset line is kicking in, and it's asynchronous, right? It doesn't matter what the clock's doing. As soon as we pull this preset line low, the device presets, which means the output goes high. Now if preset is high, that's inactive, and we pull the clear line low, right? That's a low going into this inverted input, ignores the clock, ignores D, it just immediately drives the output low. And as usual, Q bar is the opposite of Q. Now, we generally would not tell it to both clear and preset at the same time, but if you do, it says the output goes high on Q, but also goes high on Q bar, but with a little footnote saying this configuration is not stable. Right, so that's a state that we would generally avoid. Now, if the preset and clear inputs are both high, then we're neither presetting nor clearing the device. And now we can look at what happens when the clock ticks. So when the clock changes from 0 to high, if D is high, Q is high. If D is low, Q is low. And if the clock is low, then it doesn't matter what D is. The new value of Q is whatever the old value of Q is. So here they're using Q to say what will happen after the clock tick. And here they're saying, or at the next moment in time, and here they're saying Q0 is the previous moment. Right? Q0 is the output logic level of Q before the indicated input conditions were established. So this is a way of saying Q doesn't change, Q bar doesn't change, right? Because the clock is low. And the same thing happens if the clock is high. Again, it's only the transition that causes Q to change and follow the D input. So that's an example of a real-world device. So dual positive edge triggered D flip-flops with preset clear and complementary outputs, meaning that there's a Q and a Q bar available on the output side. And so they don't have a circuit diagram for this device, but they do show you, information about the different packages that are available. This is the one we use with proto boards or breadboards. This is a smaller package that we would use on top of a circuit board, so it's a very thin package, makes for a small board. But we can look at timing characteristics, right? So two parameters we're going to be very interested in. The setup time and the hold time. And so there's a signal here, right, where there's an arrow pointing up saying this is when the clock changes. The minimum setup time is 20 nanoseconds. and the minimum hold time it's saying is 0 seconds. All right, so what are setup and hold time? These are our physical devices. So let's look at a D flip-flop, and this is going to be positive edge triggered. So things are going to happen on these positive going edges. So here's the clock, here's D, here's Q. So suppose D is low. So at this point, Q is going to be low. And suppose we raise D, and so on this positive going clock edge, D is high, Q is going to go high. Okay, we know that from our table. Here's an interesting question though. Suppose right before the clock ticks, we drop D. Just shortly before. What's going to happen to Q? Well, theoretically, if we drop this 1 nanosecond before the clock tick, when the clock ticks, it should look at D and say, oh, D is a 0, and Q should go low. But that's not what necessarily happens. There's this thing called a setup time. And what the setup time means is before the clock ticks, we have to have D unchanging. So if D changes too close to the clock tick, we get unpredictable behavior. So if we want D to drop, it has to drop a certain amount of time before the clock tick in order for this device to work. And this amount of time, this is called the setup time. So the setup time says how long does D have to be fixed, unchanging, before the clock ticks. And on a physical device, we can't change D like right before the clock tick, because the circuitry won't have time to respond to that new level of D before the clock ticks. Remember, when the clock ticks, that's when it's going to take the input and latch it. But for that to happen, it needs time to look at the input and have it go through the different parts of the circuit. So there's some amount of time, nominally 25 nanoseconds, before the clock tick that D has to stop changing. So if we wanted to change D to a 0, we would have to do it at least 25 nanoseconds before the clock tick. All right, the other thing is, if we change D after the clock tick, but too soon after the clock tick, that can get us into trouble too. So after the clock tick, there's a certain amount of time that we need the clock to be stable. And that's called tau sub h, that's the hold time. And if we were to raise D right after the clock tick, like 1 nanosecond after the clock tick, it's possible that would confuse the circuitry. And when you confuse the circuitry, it might store the wrong value, but worse, it might start oscillating. It might go into some kind of unstable state. So setup and hold time are the two main characteristics for flip-flops. And basically, the input has to be stable, setup time before and hold time after the clock tip. In other words, you have to set it up this much before, and then you have to hold that value this long after. Now, beyond that, you can change D all you want, right? And before the setup time, you can change D all that you want. But this much before the clock tick and this much after, it's got to be stable. Otherwise, the device might misbehave. All right. Let me show you a circuit we can build with T flip-flops. And this is a fine circuit to build, to experiment with. But then I'm going to tell you why you should not do this. But as an illustration of a T flip-flop, this is an interesting circuit. So here's T, here's clock, here's Q, here's Q bar. I'm going to make a second T flip-flop, and here's Q, and here's Q bar. And I'm going to make a third T flip-flop, and here's Q, and here's Q bar. And this toggle input, I'm just going to tie that to a 1. So every time the clock ticks from 0 to 1, this should toggle. And I'm going to have a clock coming in here. I'm going to call this Q0. This is going to be Q0 bar. And I'm going to take that and feed it into the clock of this flip-flop. I'm going to call this Q1. I'm going to call this Q1 bar. I'm going to feed that into the clock of a third toggle flip-flop, and I'm going to call this Q2. And let's see what this does. So here's our clock. So this is where graph paper is your friend. This is why you have graph paper in your notebooks, because we're going to draw lots of timing diagrams. So the T inputs are always 1. So let's take a look at Q0. And every time that the clock ticks, Q0 is going to change. So it's going to go like this. Alright, Q0 bar is the opposite, so that's high, that's low, that's high, that's low. Now let's suppose Q1 starts off low. So what is the clock for Q1? It's Q0 bar. So every time Q0 bar rises, Q1 should toggle. So right here, Q1 is going to toggle. And then right here, Q0 bar rises, so Q1 toggles. And right here, Q0 bar rises, so Q1 toggles. And then over here, Q0 bar rises, so Q1 toggles. And Q1 bar is just the opposite. And so let's draw Q2. So let's suppose Q2 starts off low. Now what's driving the clock on Q2? Q1 bar. So every time Q1 bar rises, Q2 should toggle. And the next time Q1 bar rises, Q2 should toggle. So let's take a look at the values of Q0, Q1, and Q2. So here we've got a 0, 0, 0. Here we've got a 1, a 0, and a 0. Here we've got a 0, a 1, and a 0. Here we've got a 1, and a 0. Here's a 0, 0, 1. Here's a 1, 0, 1. Here's a 0, 1, 1. Here's a 1, and a 1, and a 1. And then here's a 0, and a 0, and a 0. So if we make a table of Q2, Q1, Q0 over time, what do we have? 0, 0, 0. And then right here, 0, 0, 1. And then here, 0, 1, 0. And then here, 0, 1, 1. And then 1, 0, 0. 1, 0, 1. 1, 1, that was a scribble. 1, 1, 0. And then 1, 1, 1. And then back to 0, 0, 0. So what have we got? We've got a 3-bit counter. Right? We have a circuit that basically produces 3 bits of output, and they change in a manner that mimics how we would count in binary from 0 to 7 and then back to 0. So this is a pretty easy way to make a counter. And you know, if we put a 4th toggle flip-flop here and connect Q bar to its clock, we'd get a 4-bit counter. And we'll actually see this in one of our future labs. There's a chip, it's a 74LS93. And it's got a clock input, it's got 4 outputs, Q, A, B, C, and D. It's got some reset lines. But if we look at the block diagram for this chip, it's presented as a series of toggle flip-flops, JKs with J and K both 1, and with the output of, you know, flip-flop B going into the clock of this flip-flop, the output of flip-flop C goes into the clock of this flip-flop, and so on. And so this is, you know, something we can do. We can build a counter like this, and we'll play around with the 7493 in one of the labs. And you can build this, right? You can take some T flip-flops and just wire up this circuit, and every time the clock toggles, you'll see the output counts. So that's a cool circuit, and it's fun to play with. But having said that, let me give you a general note to keep in mind. This is usually something we don't want to do. We don't want to monkey with the clocks on flip-flops. Ideally, we want our flip-flops to all get clocked from the same signal. And we don't want to run it through any kind of logic. We don't want to have one flip-flop clocked from one signal and another one clocked from a different signal. So in computer designs, right, part of the challenge is all of your flip-flops, you need them to be clocked by the same signal. And when you have, you know, a device that's that big, and you have a flip-flop over here and another one over here, it takes time for a signal to travel from one point to another. So how do you take a clock and make sure it gets to every flip-flop at the same time? And in the old alpha processor, there was this thing called the foot-long hot dog. And it was the clock line that traveled in a very particular pattern so that it had approximately the same travel distance from the source of the clock to every piece of the chip. And it was called the foot-long hot dog because even though, you know, it was a tiny little device, if you unfolded all of the clock line, it ended up being, you know, a foot long. And it was, you know, hot dog shaped because it had all these pathways inside to deliberately try to get it to all the pieces of the chip at approximately the same time. So this is the design we would not normally do. And let me write this down as a general edict. Don't gate the clock. So what exactly do we mean by this? Don't mess with the clock. When you send the clock to a flip-flop, it should just come from whatever the source of the clock is. And every flip-flop should get exactly the same signal. Now, having said that, it's tempting to mess with the clock sometimes. For example, how to disable a clock. Suppose we have a D flip-flop. There's a D input, there's a Q output, and there's a clock. And we want to be able to say, hey, do we want this flip-flop to load the value of D in, or should it ignore it? Well, one way to do this is to take the clock line and AND it with an enable line, and then send that into the clock. So if enable is 0, the clock is pulsing up and down, but this is a 0 coming in, and it ignores D. We've basically taken the clock out of the system. And then when we want the clock to run, we set enable to 1, and now this just takes the clock, passes it through. That will work, but it's considered a poor design. We can always make a good design, something that does not monkey with the clock, but achieves the same behavior as this. So here would be a good design that effectively disables the clock without actually changing the clock. So we could take our D flip-flop. There's the D, there's the Q. Here's the clock. The clock just comes from the clock signal, and it always ticks. And the output here goes out, but we also take that output and we send it in to a multiplexer, a 2-to-1. And so this comes into input 0, and we have some D line going into input 1, and then we have our enable, and that goes into our select line, and then our output goes into our D input of the flip-flop. All right, so what does this do? The device is always being triggered by the clock. We haven't monkeyed with the clock yet. If our enable is a 0, then the select line is 0, and this multiplexer takes this input, I0, sends it to the output. So whatever the current value of the flip-flop is, that's the value going on D, and each time the clock ticks, it just reloads the same value it's already got. So effectively, it's ignoring the D input. The clock is still ticking, but it's as if the clock has been paused. Now when we want to actually load in the D input on the next clock tick, what do? We set the enable line to 1. Well, now this multiplexer takes the D input and sends that to the output, which goes into the D input. So once we set enable to 1, the next time the clock ticks, this value is sitting here on D and it gets loaded into the flip-flop. So this is a good design. This is synchronous. This is honoring the clock. It's paying attention to the clock, whereas this is in some cases stopping the clock from triggering this device. So when we look at more complex circuits, when we play around with Verilog at the very end of the course, we'll see a lot of examples of this kind of design. And if we try to design a circuit like this, we'll actually get warnings from some of the tools saying, you know, this is poor design choice, you shouldn't be doing this. So that's something to keep in mind. And there's some questions where we ask you to create new circuits out of other kinds of circuits, and there may be cases where you can do it by manipulating the clock, but see if you can do it without manipulating the clock. Leave the clock as is, but add some other circuitry. All right, last thing I want to mention is just this idea that, you know, most of our circuit design is done with clock-based systems. We have, you know, billions of transistors making logic gates and memory units and so on and so forth. And the general rule is when the clock ticks, things happen. And, you know, inputs go through circuits, come out outputs, and those feed other inputs and so on and so forth. And eventually, everything should stabilize. And it should stabilize before the clock ticks. And then once everything has gotten to the point that it's going to get to, then the clock ticks and the next set of things happen. So that's synchronous design. We can do asynchronous design. You can design circuits without clocks. And theoretically, they can run faster because once you set your clock speed, things are not going to happen faster than that. But in asynchronous design, where there is no clock, you can let things just happen as quickly as the hardware will let them happen. But it's phenomenally difficult to design without that clock. And most of the work that we do, most of the tools that we have are built around the idea of synchronous design. So asynchronous is you know, a whole nother frontier. People explore it, people work in it, people have built systems that run asynchronously, but it's a very different kind of landscape. All right, so that's all we've got for today. Next week, we're going to start developing state machines using these flip-flops and this idea of synchronous logic. And that will be the next big piece of the course, is state machine analysis, looking at state machines and understanding them, and then synthesis, taking a goal and designing a state machine to realize that goal. So we'll be doing all that starting next week.